Hello everyone, my name is Min Lu. In this section, I will give you a tutorial for conducting multivariate meta-analysis in R with the package metavcov. Suppose we have several outcomes or several effect sizes. We can conduct separate univariate meta-analysis for each of the outcomes. Or we can conduct a multivariate meta-analysis, MMA, for pulling the estimated effect sizes simultaneously using one analysis. The difficult part is that we have to compute the variance-covariance matrices among all the effect sizes for each of the study. Okay? Which is in the first steps in the MMA. So there are 3 steps for conducting MMA, and in this tutorial, I will use different R packages for illustrating them. The difficult part is still the first part because we have several effect sizes. They could be measured differently. For example, some of the effect sizes might be evaluated as log odds ratio for kind of binary outcomes, or some of them may be evaluated as mean difference or standard mean difference or correlations. To compute the variance-covariance matrices, we have to use different functions. The good news is that once we compute the variance-covariance matrix, all the R coding for the second step or the third steps are kind of the same. Okay. So now let's go to the R Studio for a real data application for standard mean difference. Here are the formulas. First, let's load the package. And then if you haven't installed the package, you can install it through packages install or using R command. So after you load the package, you can load the data. Here's the data where you can see we have many columns. For this illustration, I will only use 2 effect sizes. Okay. Here is the data where we're comparing the treatment effect of a specific drug for 2 outcomes. One is systolic blood pressure, SBP, and the other is diastolic blood pressure, DBP. Okay, so here is the data we have. We actually have 17. We have 21 studies. So to conduct a multivariate meta-analysis, we have to know the correlation between these 2 effect sizes. In the original data collected in 2010, there is no correlation recorded, so I kind of impute a constant for this correlation based on previous literature. So here is the correlation matrix for the 2 outcomes. Ideally, this correlation should be different from each study, okay, recorded from each study. Since I don't have this data, so I impute this constant. The function for computing variance-covariances for standard mean difference is called smd.vcov, where we have to tell R the number of treatment, the sample size in the treatment, and the sample size for the control group, and the standard mean difference, and the correlation matrices I just mentioned, and the name of the outcome. Okay. After computing the variance-covariance matrix, the effect sizes are saved in this object EF. Okay, that's EF. Okay. Now I want to explain the format for the variance-covariance matrices for the effect sizes. Suppose we have 6 outcomes from n studies, then we can have n 6 by 6 variance-covariance matrices. Okay. In R, there be a list of matrices, or we can record what is called flattened variance-covariances, which basically read in the elements for each column in the lower triangle, since this variance-covariance matrix is symmetric. In other words, if we have n studies, then we have n rows in this matrix. In R, they will be saved as a matrix dot VCOV, which is a variance-covariance elements in a flattened fashion, or list.VCOV, okay, which you have matrices of variance-covariance matrix, symmetric variance. If you look at the first row, you can see they are the same. Okay. So we finish the first step. Basically, we compute the effect sizes, we compute the variance-covariance matrix. Now we go to the second step, where we fit the model. To fit the model, there are two fashions. You either use fixed effect model or use random effect model. Okay, they based on different model assumptions. We can use a metavcov, okay, where we use Y to name the effect size and use S to name the variance-covariance matrix for the effect sizes. And here is the R code. Okay, fitting the model is kind of simple. Only kind of need one line of R code, where we can check the Q statistic, where if the p-value is smaller than 0.05, then we should use a random effect model. Here, our p-value is larger than 0.05, so a fixed effect model seems sufficient, which has higher power. An alternative way is to use a package called mixmeta, okay? And the R code also very easy. Basically, you tell the data, which is the effect sizes, the variance-covariance matrices, and then, sorry, I forgot to run. The about line. So now we have the only difference is we have this line of formula. Basically, we estimating the mean, which is kind of fitting a regression model with the intercept only. Okay, here is the outcome. Here is the output, which is similar as before. Okay. Although for this specific data set, fixed effect size models already sufficient, but I want to illustrate a random effect model just for the purpose of illustration. We can also use the package mixmeta. Okay, you can see the R code is the same, except we have method REML instead of fixed. Okay, that's here is the only difference. Here is the result. Okay. Alternatively, we can use a package called metaSEM. Okay. Where we have this similar type of fashion, where the input is called Y instead of data. Again, variance-covariance matrix. And here's the result. Okay, here's the result. So basically, we finish the second step where we obtain the estimated effect sizes with standard error, confidence interval, p-values, etc. After reporting that, we can make some plot with metavcov in the function plot ci. Okay. Here we have two outcomes as BP and dBP. Here is the R plot. Okay, we can stretch a window for the figure and click export to save in your local computer, paste in your manual script, or you can kind of uncomment these two lines of R code to save it in a PDF document. Okay, very easy. Okay. So here I use the original name of the Y. You can put it more English here. Okay, in a R vector. Okay, in a character vector. Now we go to our second example, which is correlation coefficient. Here are the formulas. Okay. The only thing I want to mention is that here we have this graph dataset where we have 4 outcomes: athlete performance, 3 subscript file anxiety. For 4 outcomes, we have 6 correlations, and then you put tell R of this effect sizes in a kind of flattened format where you tell R the coefficients, correlation coefficients, one by one in this order. Okay, in the lower triangle. What happened is the order of these correlation coefficients corresponds to the subscripts in this formula. You have to input it in this order. That's the only difference from other effect sizes. The function for computer variance-covariance matrix is called r.vcov. Instead of previously we use SMD VCOV. Okay, we use a different function because we have different inputs. The inputs kind of simple. We only need the sample size and the effect size. Okay, sample size and effect size. Again, we use Y to save the effect size, use S to save the variance-covariance matrix. Okay, model preparation is done. Then we fit a random effects model, just like before. Okay, nothing really different from the previous example. Okay, maybe the difference is that previously we only have 2 outcomes, now we have 6 outcomes. Okay, but the R code kind of similar. And we can also conduct a meta regression. Okay, where we have this formula to tell R, what is a predictor for all the 6 effect sizes. Okay, when you look at the output, you can say for each effect size we have intercept and we have the slope for P male, percentage of male. Okay, let's look at the data. So here in the data we have effect sizes, and then we have column called percentage of male participants for each of the study. So here we can say if it makes a difference on the correlation coefficients. All similar as before, we can use a meta function from meta-SEM. Okay, easily similar. The next example is about correlation coefficients from multiple imputation. Okay, one problem for multivariate meta-analysis is missing values, and then we can use multiple imputation for this type of data set. First of all, I kind of mimic the scenario of missing values. Okay, here I mimic some missing value, and then I will use a function called meta-mi from package metavcov. Okay. To use this function, I have to tell R, what the column name for the sample size and what the column name for effect size is. Okay. Here, I have to pull the result from multiple imputation. Here is the result from a fixed model with meta-fixed function we used before from metavcov package. We can also use a plot for this pooled result. Okay. Here we have 6 outcomes, so we have six effect sizes, so we have like 6 figures. Okay, just like before. When there are missing values, then the confidence interval part will be empty. Okay. Again, now we have this random effect model, okay, where we still use this meta-mi function. The only difference is that here we use function meta from meta-SEM model instead of meta-fix. Or the other part kind of similar. Okay. So here is the pooled result, and we can also have meta regression. Okay. Okay. Here is a intercept, and here is a slope. Okay. This is for the purpose of illustration. Here, basically, I think the model have converging issues. Now, the last example is basically to give you a little bit flavor about effect sizes of different types. We have different functions for different types of effect sizes. Okay, so the function with underscore basically only used for compute the pairwise covariance, pairwise variant covariance of different types, usually working for one study. Okay, if you have data collected for several studies, we basically use this mixed.vcoa function. We still use our first data set, but we have 4 outcomes to look at. Okay, the first step still I'm imputing the correlation among these 4 effect sizes. The 4 effect sizes will be mean difference, risk difference, log odds ratio. Basically, the first 2 effect sizes are continuous. For continuous outcomes, then the last 2 effect sizes are measuring binary outcomes. For all these 4 effect sizes, we have to give them different inputs one by one. Okay, if it's not valid, then you should put an A. For example, D is for continuous outcome difference. Okay, either mean difference or standard mean difference. It doesn't work for risk difference or log odds ratio, so you put an A there. ST is events in the treatment group. So there's no number of events for continuous outcome. Okay, continuous outcome for SMD and DMP. So you put an NA there. And for the other 2 outcomes, then you put the corresponding number. Okay. So after running here, you detach the data. Now you have the computed effect sizes, still saved in Y, and computed variant covariance saved as S. Okay, so here is the variant covariance matrix labeled with like either variance or covariance among 2 variables connected with underscore. again, once you have Y and S, all the R code kind of the same. Step 2 to 3 kind of the same, in the same fashion as before. Okay. Thank you very much. And here are all my references. I basically focus on 3 packages where you can contact the maintainer directly for specific questions. Thank you very much.